everyone. In this video we're going to work on the second example from 1.1. So we worked through just a preview activity to try and get the idea of what an antiderivative was. And we've even defined at the top of the page here that the antiderivative of function f is not just a function whose derivative is f, but it's a general form of all possible functions whose derivative would be f. Okay, so once again, and like I said, this will be true for a lot of things, I'd like you to pause and see if you can kind of work your way backwards out of these on your own. Some of them get a little messy towards the end, so feel free to check back in and see if I can help get you started, but you want to do as much of this on your own as possible. So even if you're checking back in, just get to the step you were stuck on, and once you see that step, try and pause again and finish the problem on your own. You will learn so much more if you really try and work through and think about these on your own. Okay, so the antiderivative of each of the following functions. First function, and actually this really throws people sometimes, the simplest functions can be the most confusing. So first function A, I'm going to switch back my colors, is just a constant function. So we're thinking about what do we take the derivative of if we want to get a constant. One way to think about that is graphically. So if we're talking about the derivative being constant, oh, and I suppose I should draw it below since this is f of x equals negative 1/3. So if our derivative has a constant y value, then the function that we started with has a constant slope. So this will be big F that we're talking about. Big F has constant slope equal to negative 1/3. So if we're looking for a function that has constant slope, that is by definition a linear function. So we know that to get constant function f of t equals 1/3, we would have taken the derivative of linear function with slope of 1/3, and the y value does not matter as long as the slope is negative 1/3. The derivative will be negative 1/3. So any y value you want on there and you will have the right answer. And again, with this whole antiderivative business, that means that there's a function that looks like this that is an antiderivative. There's one that looks like this that is an antiderivative, and there's one that looks like this. So these are all just different plus c's. Pretend this one actually hit the origin. So this could be like a c equals 0, this could be a c equals 1, this could be a c equals negative 2. So the function will have the same basic shape, but could be shifted up or down and still be one of the antiderivatives. Okay, the next couple tend to be the ones that people are best at. So reversing the power rule is one that people tend to be really good at. Just make sure that you think about some of the other possibilities as well, because we will have more right off the bat. Give me just a second to get there. So if my function that I'm starting with is g of x, little g of x, and I want to find the antiderivative, so I'm going to call it big G. Again, that's not a rule, it's just kind of a convenient bit of notation. I'm asking myself, who do I take the derivative of if I want to get 2x? So here's a little more clear product rule happening. I'm sorry, product rule, power rule. If I think about that as 2x to the 1, I know that I needed to start with some sort of second power in order for the power rule to leave me with a first power when I'm done, if that makes sense. So when you take the derivative, the power reduces by 1, which means when you take the antiderivative, the power is going to increase by 1. And then there's just a little bit of trial and error in checking to make sure that you don't need to adjust the coefficient. So yes, x squared will leave you with an x to the first. Does it leave you with 2x to the first? And the answer here is yes, so we could do a little check. You can do checks for both of these off to the side. So for this one, my check is g prime of x, the derivative of x squared is 2 times x to the 1, which is great. I'm not completely done with that one. I do need to throw on my plus c, but that's looking pretty darn good. Really quick, let me sneak back since I forgot. Our check for the first one is find f prime of t. And again, we talked through this pretty carefully, but you can just do this with Calc 1 shortcuts. And you can even do it with a power rule. You can think about that as a t to the 1. So the 1 drops down in front. You still have the negative 1/3. and then you get a t to the 0, which actually just equals 1 as well. The derivative of a constant is always 0, so we're good on that one. Okay, so this gets slightly trickier. It's still linear, which means I'm still expecting for part C to get a quadratic as my antiderivative. If you take the derivative of a quadratic function, you should get a linear function. What gets a little trickier here, a couple of things. We have the plus in the middle, but just like the plus is really simple when you're taking derivatives, it will be really simple when you're finding antiderivatives as well. So if you want the antiderivative of a sum, you just look at each of the pieces individually. So I'm going to start with a 5y. So if I want the antiderivative of 5y, just like before, I can guess that I need a y squared involved, but I already know that when I take the derivative of y squared prime, did I make a big deal out of this prime notation, or am I just making it up? Oh, no, never mind, my brain is crazy. I've been doing Calc 1 today as well, and all of a sudden I felt like I was teaching Calc 1. You guys already know about primes. Okay, so if I want the derivative of y squared, it's a 2y. The y part is great, but I didn't want a 2, I wanted a 5. So this is where it becomes a little bit of trial and error. You say, okay, if I have a 2 and I want a 5, you can ask these in either order, but I'm going to say first, how do I get rid of the 2? And the answer is you multiply by a 1/2. So over here on my check, now if I say I'm taking the derivative of 1/2 of y prime, I'm going to get a plain old y, which is great, better, not perfect. So now that I got rid of the 2 that I don't like, I would like to introduce the 5. And I'm going to introduce the 5 just by throwing it into the top of that fraction. And when I do that, 5 halves, I'm going to have the derivative, the 2 will drop down in front, it'll cancel, and I will be left with the 5 and the y, which is excellent for the first part. I still need to deal with the second part. So the second part is, what is the antiderivative of a plain old 3? And the answer is, it's a 3y. So that's back to that. If you have a constant, the antiderivative should be linear. And then we have to add our c, and we can tack on the rest of this to our check. So let's see, I'm going to erase this mess a little bit. Do our full check. Whoa. It's getting laggy. Okay, so our check here is h prime is equal to, okay, we already checked this out fairly carefully. If we bring the 2 down when we take the derivative, it'll cancel with the 2 in the bottom. We'll be left with the 5 and the y. And then when we take the derivative of 3y, we get 3. When we take the derivative of c, we get 0. This is perfect. Okay. M of k is equal to 2k to the 4th plus k cubed minus 7k. Okay, so stepping it up a little, but we're still doing power rules. So all of these so far have been power rules. Generally, people are good at reversing the power rule. So here's my thinking. Again, the big operation is the plus minus, so we need to think about that first, but that's really easy. That just means we're going to take the antiderivative of part 1, part 2, and part 3, and then just add them back together. And we know we're right when we do that if taking the derivative really does get us back what we wanted. So if I want to end up with a 2k to the 4th, part of that I can get fairly easily. I know that I need to start with a k to the 5th. And then if I think about taking the derivative of the k to the 5th, the 5 would drop down. I would get a 5k to the 4th. Not exactly what I want, but pretty close. So just like before, I would like to get rid of that 5 that drops down in front. So I'm going to put a 5 in the denominator of the coefficient. Now, if I drop that down in front, I get 5 over 5k to the 4th, which is 1k to the 4th. Just still not quite perfect, but it's pretty close. I just need to introduce the 2. I just need to introduce the 2. So now it would drop down to the front, the 5s would cancel, I'd have 2k to the 4th. First part looks good. Note that the reason that this is so simple to tweak is because constant multiples, so coefficients, just carry through when you take the derivative. They just hang out in front. You don't have to do a product rule. You don't have to do anything weird, which means the same will be true when we go the opposite direction. We can just tweak those constants out in front, the coefficients, as much as we want. The lonely constant, the plus c, that derivative is just going to be 0. The constant multiples, things like the 3 and the 5/2 from part C, those are the ones that are going to come along for the ride. Okay, so moving on to a k cubed, I can guess that I want a k to the 4th. I can start thinking about what happens when I take the derivative. That 4 would come down in front. I'd have 4k cubed. I don't want a 4 out in front, so I'm going to divide by that. Now when I bring the 4 down, I'm going to get 4 over 4k cubed, which is a 1k cubed, which is perfect. I don't have to introduce any constants that I want, any coefficients that I want, so I'm just going to keep that a 1/4. And then last piece, 7k, so we know if we want to end up with a k, we should have started with a k squared. If we think about that power rule, the derivative would be a 2k. I don't want a 2k, so I'm going to divide by the 2. So now I'm down to, when I take the derivative, I will get 1k. I don't want 1, I do want 7, so I'm going to make that a 7/2, and then a plus c. And again, to write out my check a little bit more fully, when I take the derivative, I don't have much room, so I'm just going to pencil in over here. So this is my m prime. The 5 comes down in front on the first one. I'm left with a 2 and a k to the 4th. The 4 comes down on the second one. I'm left with a 1 k cubed. The 2 comes down on the third one. I'm left with a 7k. And then the derivative of c is 0. And again, remember what we're looking for is that the derivative matches up with the function that we started with. Okay, 3 more. The middle 2 are a little tricky. Okay, so this one, the reason it's tricky, here I even kind of want a whole different color here. Let's choose color number 3. Maybe a green. Okay. So the reason it's tricky is just because you need to rewrite the original function before you jump into finding antiderivatives. So remember that this is the same as x times x to the 1/2 plus 1 over x times x to the 1/2. So what I'm doing here is not finding antiderivative or derivative, it's just rewriting original function n, little n. So little n is my green stuff. Remember, you can add exponents, so this is the same as x to the 3/2, 1.5. plus 1 over x to the 3/2, which is the same as x to the 3/2 plus x to the negative 3/2. This is an ideal form for finding antiderivatives. So let's go ahead and switch to blue for our antiderivative. If I want to find this big N of x, big operation is addition, so let's look at one piece at a time. X to the 3/2, so that's still a power rule. It's a trickier power rule, but it is still a power rule. We're going to bump that power up by 1 and say, okay, if I'm going to get a 3/2 power, I need it to start with the 5/2 power. But we know, now I got to go find my pink again. Pink. Okay, oops. We know that when we do the power rule, that's going to give us a 5/2 x to the 3/2, which is not quite right. I'm blocking it. We want a 3/2 when we're all done. Oh, I'm sorry, we want a 1 times x to the 3/2 when we're all done. So if we have a 5/2 that's coming down, we need to cancel it. We need to basically divide this thing by 5/2, which is the same as multiplying by 2/5. So we need to multiply by the reciprocal, and hopefully you can see there that when the 5/2 comes down, we're just going to get a 1 out in front and then an x to the 3/2. For the x to the negative 3/2, same idea, but people get a little messed up by negatives sometimes. If we want to end up with an x to the negative 3/2, we need to bump that power up by 1, which bumps us to negative 1/2. So don't go the wrong direction. People a lot of times want to make it negative 5/2. That's backwards. Okay, so right now, if I did my power rule, I'd get negative 1/2 x to the negative 3/2. I don't want a negative 1/2. So to cancel out a negative 1/2, I need to throw a negative 2 out in front. That 2 and that negative are ugly. What in the world is happening with my pen? 2. Okay. Oh, plus C. I almost forgot. Don't forget your plus C's. When we go to check n prime, we're going to bring that 5/2 down, multiply it by the 2/5. That's going to give us a 1 times x to the 3/2. We're going to bring the negative 1/2 down, multiply it by negative 2. That's going to be positive 1 times x to the negative 3/2. And, oh, no plus. The derivative of c is 0, so that is all gone. I don't have a ton of really picky simplification things, but I do have a couple. One is I don't want you to leave me with fractions and fractions. And another one, because it's generally a way that people will get around fractions and fractions, try to get around it, is I don't want negative exponents. So I would prefer that we rewrite this as 2 over x to the 1/2. I do not have a preference on whether you write that as x to the 1/2 or the square root of x. It does not matter at all to me, but I do want to see you deal with negative exponents. Okay, couple more. Sorry, long video, I know. P of t is equal to t squared minus 1 over t all squared. Okay, so for starters, I was mean and I used a capital, but I did it on purpose because I want to make the point that there isn't a rule that you have to start with a little p and end up with a big P. So let's call this whatever we want. I'm going to call it Q when I go to find the antiderivative, but I'm getting a little ahead of myself because this is actually similar to the last one where we need to do a little bit of rewriting before we can do any antiderivative. Okay, so, I'm getting a little scrunched here. With this one, there's a couple of things that need to happen. So, I don't know what order we want to do this in. Let's do this. If we are squaring the whole fraction, we can split that up and say this is the same as t squared minus 1 squared over t squared. We'll just sneak down below here. Which means if we FOIL that out, remember you can't distribute the powers, it's not t to the 4th minus 1, you have to think about t squared minus 1 times t squared minus 1, so there is a t to the 4th, but there's also a negative t squared minus another t squared, so a negative 2t squared, and then there is a 1 in the mix, all over t squared. Okay. And I like this a little better because I don't really know how to easily reverse having everything raised to a power, but I also don't know how to easily reverse some messy quotient. So it may have come out of some quotient rule or something like that, but that is not that easy to spot. So I still have a little bit more that I can do with algebra. Whenever possible, make your life easier using algebra. And the little more is you can always split up the numerator of a fraction. So I can split this up and say this is t to the 4th over t squared minus 2t squared over t squared plus 1 over t squared. So running out of room. Which is the same as t squared. T to the 4th over t squared is t to the 4 minus 2 minus 2. T squared over t squared cancels completely. All right, so here we're saying 2 of these are left over. Here we're saying none of them are left over, and then the 1 over t squared, there's no canceling, but just like in the last one, it's much easier to deal with if you make that a negative power. Okay, so now that I squeeze that in, let's switch back to blue. Now I'm ready for antiderivative, so we're going to look at each of the 3 pieces separately and then attach them by whatever operation's in the middle. A t squared, I know I'll need to have started with a t cubed. If I have just a t cubed, that'll work, yes. Okay. If I have just a t cubed, then when I take the derivative, I get a 3t squared. I don't want that, so I'm going to throw a 1/3 out in front to cancel it. Ooh, battery's running low. I don't know if you can see these things, but you probably hear chimes going off. Okay, the -2. If we're going to end up with the -2, we need to have started with a -2t. And then the t to the -2. Again, be really careful with these negative powers. We need to increase our power by 1. 1 more than -2 is -1. And I want to think again about if I bring this down in front, nothing weird happens with the t to the 1, but with the t to the -1, I would get -t to the -2, and I don't want a negative out in front, which means I have to throw in an extra 1 to cancel it. So this is what I think my derivative, or my antiderivative, is looking like, plus c, which means rewriting, you can make it t cubed over 3 if you'd like, minus 1 over t would look like this. And then on my check, I would say from either one, q prime is equal to 3 times 1/3, which is 1, t squared, minus the derivative of 2t is just a 2, and then minus the derivative of t to the -1, which is -t to the -2. Those two minus signs will cancel each other out, and this is exactly what I started with, so this is looking great. Okay, last one before my battery dies. This one is actually less tricky than what we've just been doing, but it totally throws people off. Let me go snag my green. There's a tiny bit of rewriting that I can do. Well, actually, maybe even more than a tiny bit if needed. For starters, that 2 is really easy to separate out. And then the second thing is always be on the lookout for this one. 1 over cosine squared is the same as secant squared. And secant squared, I think, is much more, plus theta, not c, much more easily recognized than, hey, remind me while I mess with my colors. Here. Much more easily recognized than cosine squared as the derivative of tangent. So if I'm looking at this thing, I'm going to say big R of theta. So the antiderivative of -1/2 secant squared theta is going to be -1/2, which just stays exactly the same, times a tangent theta. And you just have to remember this. We're reversing our basic derivative shortcuts. So in Calc 1, you should have been shown that the derivative of tangent is secant squared, and exactly why that's true as well. So now we're just remembering that and using it to find antiderivatives. And then the theta, because it's a different variable, sometimes people think that's harder than it is, but it's just like before when we had a t or an x. If you want to end up with a theta, you better have started with a theta squared, but the power rule would drop that 2 out in front and make it a 2 theta, and we don't want that. So we're going to throw in a 1/2, and then we're going to do a quick double check and say r prime of theta is equal to -1/2. The derivative of tangent is secant squared theta, and then the 2 comes down in front. 2 times 1/2 is 1, so we're just left with a theta. Derivative of c is 0. Okay, so really long one. Hopefully that made sense. Thanks for watching.